So here we have a question that's basically got us to do some bit of induction as well as some graphing and then some sort of region as well in terms of area. So a little bit of a mix. Now, the first question asks us, you've got a function fx equals e to the px x plus 1, where p is a non-zero number. Show that f dash x equals that. So you just got to derive that. And then you'll need to show the nth derivative is this using induction. So let's focus on those for now. Fx is e to the px times x plus 1. If you're trying to derive this, first thing you'll note is that it's a product. It's e to the px times x plus 1. So that means you would need to use the product rule. So you would derive the first one, which is p times e to the px, multiplied by the second function unchanged, which is just x plus 1. And then you would add the derivative of the first one times the second function unchanged. And so that would be what you have there. And then you can just factor out e to the px, leaving you with p x plus 1 plus 1. And that's your answer to part 1. Now, you're then basically asked to show that the nth derivative is in other words, the nth derivative is this expression here. By induction. All right, so we'll need to use part 1 we've already got, but we'll need a bit more space. So let us minimize that a little. So first things first, we need to show for n equals 1. So for n equals 1, it's true, right? Because for n equals 1, p to the 1 minus 1 is just 0, p to the power of 0, so it's 1. So we've got e to the, well, px times px plus 1, which literally is just what we showed earlier in part 1. So for part 1, it's true due to part 1. So we won't redo the working for that. We'll basically show that it's true for n equals 1. That's fine. So we'll assume true for n equals k, where k is a positive integer. I'll just save the writing on those details here, but we'll assume it's true for n equals k. In other words, fkx is p to the k minus 1, e to the px, px plus 1 plus k. And we need to show that f of k plus 1x is p to the k plus 1 minus 1, so p to the k, e to the px, px plus 1 plus k plus 1. All right, so that's our job. We need to show that. Well, how would we show that? Well, this, by definition, has to be the derivative with respect to x of the kth derivative. Right? The k plus first derivative is the first derivative of the kth derivative. Now, we don't know what the kth derivative is, but we've assumed it's this, right? We've assumed it's this thing over here. And so we can sub that in. Okay, so we're trying to derive this thing. Okay. We're trying to derive this. You've got the k plus 1th derivative, and we want to ultimately show it's this. All right. Now keep in mind, you're deriving with respect to x. So particularly when we're doing questions like this, where you've got a whole lot of letters, keep in mind what you're actually deriving with respect to. And like when you're doing maximum problems, keep in mind what's a constant. K is a constant. P is a constant. So this whole thing here is a constant. And E as a number is also a constant. The only variable, so P, K, E are all constants. Your only variable is X. And you're only deriving those functions. So keep that in mind. So because of that, we can basically take P to the K minus 1 out. That doesn't matter. And then you're deriving this thing inside. And then as before, you would recognize, hopefully, that this is a product because you've got e to the px, which is an exponential in x, that there is a variable there. And then you've just got this thing, which is basically, well, px plus p plus k. So you've got two functions here that are multiplied by each other. So we'll just apply the product rule. So moving on to a new page. So you would, I'll write this out here. So if I do that as blue, if I do this as sort of green, then it may be helpful to separate this out if it's confusing. If you're happy to do it directly, then feel free to do so. Right? Because basically, the derivative of k being a constant is 0, and the derivative of p of x plus 1 is, well, 1. So you've got p times 1. So putting all of that together, you've got p to the x minus 1 all multiplied by the derivative of the first times the second unchanged, plus the derivative of the second, which is just p, times the first unchanged. And from there, you can factor out p. You can also factor out e to the px. So we'll have px minus 1. We've got p, we've got e to px, leaving you with px plus 1 plus k plus 1. Which then means we've got p to the, that should be a k minus 1 all the way back here. Just the transcription error when I copied from before. So k minus 1 times p, it will be p to the k, e to the px, and then of course we can just write this as px plus 1 plus k plus 1. And if you just to compare against what you wanted, this is what you needed, right? Equals right-hand side, as required. And therefore, because true for n equals 1, true for n equals k and k plus 1, therefore true for all positive integers n by induction. You can write a longer conclusion. That's really not the key point of this question, so I'll leave you to do that. But basically, we've proven it's true for n equals 1 using part 1. We've assumed it's true for n equals k, where k is a positive integer. And we have now shown, by using our induction hypothesis and through deriving, that it is true for the next one. So we've now, therefore, proven it. So the next question then says, when p equals root 3, so when p equals root 3, the graph of the function has exactly one point of inflection. Without proving a change in concavity, find the exact value of the x-coordinate of the point of inflection. Okay, so what do we have when p equals root 3? We'll firstly write out our function. Our fx was e to the px times x plus 1, But for this question, p equals root 3. So that means it's e to the root 3x, x plus 1. And it has one point of inflection. You want to find the exact value of the x-coordinate of the point of inflection. Okay, so basically, for an inflection point, we understand the second derivative equals 0. They kind of give you an out. They say, don't prove that there's a change in concavity. Basically saying, don't bother, just, find the second derivative equals 0. So let's do that. Now, we could, of course, find the first derivative and the second derivative, but let's not waste our time. We know the second derivative, based on part 2, is going to be p to the p to the power of 1 times e to the px, and p x plus 1 plus 2. This is for n equals 2 from part 2. So that's the second derivative for any p, right? We've subbed n equals 2. And so that saves us a bit of work. Obviously, we could have also derived it. We can sub in p if we like. It's not really critical at this point. We will need it at some point. But the key thing is we want to solve for this to equal 0 because it's a second derivative and you want to find your inflection. So, and now taking a look at this. For this expression, which is your second derivative, to equal 0, you've got it as root 3, which is not 0, times an exponential, which can never equal 0, times this thing equaling 0, which of course means the only way that can happen is this equals 0. So just solve for x. So it's negative 2x plus 1 equals negative 2 over root 3. X equals negative 1 minus 2 over root 3. And that's your x-coordinate. Of course, formally, we have not shown that this is an inflection point. We would generally need to prove that there's a change in concavity. But the question has told us, don't bother with that. So this is all they're wanting. So this is the exact value of the x-coordinate of the point of inflection. Secondly, they now ask us to consider further a different p. So that's that part of the question. The next part of the question says, consider the function when p equals a half, and they've written out the fx for you. The graph of y equals e to the x over 2x plus 1 has a minimum and a max and an inflection, and they've worked that out for you. So sketch it, showing stationary point, inflection point, intercepts with coordinate axes and any asymptotes. So basically, they've done a work for you. They've done a lot of the work for you, and they basically want you to put it together and sketch it. So let us consider what we know. So we know that fx, which is what we're trying to draw, is e to the x over 2, x plus 1. You have been told that there's a minimum at negative 3, negative 2 over e root e. You have also been told that there's an inflection point at negative 5, negative 4 over e squared root e. Okay. Now, we need to work out asymptotes and also intercepts as usual. So for x equals 0, you're just going to get 1. Easy enough. You just sub it in. So that's your y-intercept. Now for y equals 0 or fx equals 0, I mean, just a quick look at this would suggest you know that this times this equals 0. E to the something is never 0, so the only way is x plus 1 equals 0. So x is negative 1. So you have both your x and y intercepts. It would also be helpful to basically take some limits. So the limit as x approaches infinity of fx, well, if you're going to positive infinity, then that goes to positive infinity. That goes to positive infinity. So that suggests fx goes to positive infinity. So it doesn't approach a limit, it just goes up all the way up. The limit as x approaches negative infinity. So when you go to negative infinity, this will go to negative infinity. This will go to 0. And then you have this problem of, okay, I've got 0 times negative infinity. So you've got a really small number times a really big number. And then the question is, okay, if you've got a small number times a big number, it's not really clear if it's positive, if it's big or small. Look, it's very clear it's negative because you've got a positive number times a negative number. And it might not be clear to many students whether this is positive or negative. And this is where you need to kind of have an idea of hierarchy here. So an exponential, if you're sort of fighting an exponential versus a polynomial, is a polynomial power 1, degree 1. So the exponential will win. So basically, this is 0, this is infinity. They're going towards different ways. The exponential will win out. So it will be a small negative number. But it's going to be negative for sure. So with all of that information, we should have a decent chance of graphing this now. So we'll put in the information. We know as you go to infinity, it goes into infinity. We know as it goes to negative infinity, it goes towards 0. We know you've got 0, 1. We know you've got negative 1. So you know you've passed those points, just as a rough guide. Now you know you have a minimum at -3, -2 over e root e. You might want to use a calculator to get some idea of what number that might be. And that's a really decently small number actually, -0.44. So it looks like it's around here, not to scale. And then you've got -5 and -4 over e root e, e squared root e. So that's about here. Okay, so it basically looks like you're going to have a concave down, concave up curve from here. So that's the general gist. We'll obviously draw it a bit better now. So now that we've kind of got that in mind and have a better idea of that, let's rescale everything. So that's that sort of idea. It's not to scale still because that -3 is too far down. But something along those lines is not really quite to scale because as we've worked out, that's about 0.44. So this is too far down, but certainly the shape and so forth is what we're looking for there. If you have a ruler, then you should try and draw it a little bit more to scale than I have done here. But do ensure, of course, that your points are all in the right sort of place relative to the origin. And then it's a question of how close to scale you can get it. Making sure you've paid attention to, the inflection point, the minimum, and so on. Okay. The question then tells us that the derivative of e to the px over px plus 1 minus e to the px over p squared equals this. You're not required to prove it, I'm just telling you, because presumably you need to use it. Then they ask this question. Let R be the region enclosed by the curve y equals e to the x over 2 x plus 1, which we already have drawn. Keep that in mind. We drew that in the earlier part. The x-axis, and then lines x from -2 to x equals 2, and show that that's the area. Okay. So it would be helpful to refer to our diagram. You want the region R to be enclosed by the curve, okay? The x-axis, okay? So x-axis is over here. And also the lines x equals -2 to x equals 2. So that's interesting. -2 would be here. 2 would be here. Assuming we haven't made any mistakes in our drawing, then that implies that they actually want 2 different areas. Okay, so if you've got these areas, then it would appear that you're just trying to integrate from -2 to -1 and from 1 to 2 with the respective versions. So the region R is composed of 2 areas. Area 1 is going to be, I guess, the integral of f of x dx from -2 to -1. And so you can see from -2 to -1, and then it's going to be below the axis. So it's going to be the absolute value of that, which we also know is going to be the negative of that because it's below the x-axis. Area 2 will be from -1 to 2 of fx. All right. Now, we also know, of course, keep in mind what we already know. So fx in this question is e to the x over 2x plus 1, and you are specifically told that the derivative of e to the px over p, x plus 1, minus e to the px over p squared equals e to the px, x plus 1. So if you are told this, then noting, of course, that e to the px times x plus 1 is, well, basically your fx. So if the derivative of this is that, then another way to think about this is that the integral of e to the px is equal to this here on the left. The derivative of this is that, so the integral of this is this, you know, with a plus c, but we've got definite integrals here, so it doesn't matter. And if you just do a quick comparison, our p is a half. So e to the x over 2 x plus 1 dx is equal to e to the x over 2 over a half, which is 2 x plus 1 minus, well, a half squared is a quarter, divided by a quarter is 4, so minus 4 e to the x over 2. So we don't really need to integrate because they've given us the integral. So we just need to basically sub those values in. So the integral of fx is 2 e to the x over 2 x plus 1 minus 4 e to the x over 2, -1, -2, plus the same thing, -2 and -1. All right, so let us work out area 2 and area 1 separately. So that means I'm going to have 2 e to the -1/2 comes 0 minus 4 e to the minus 2e to the -1 times -1 minus 4e to the -1 with a negative at the front. So just be careful. Negative of negative is plus, but that's got a negative there. So negative 2 over e. And then, so that's plus 4 over e, right? So negative is plus, plus with that is going to be minus 4 over e. And then you're going to have negative of this. Well, that's just 0. So we've got negative of negative is plus 4 over root e. Okay, so that's going to be negative 6 over e plus 4 over root e. And we may want to write that all over e for now. So that's going to be negative 6 plus 4 root e over e. That's area 1. Area 2, bit of subbing in. It's got 2e to the power of 1 times 3 minus 4e minus 2e to the negative half times 0 minus 4e to the negative half. So that's 6e minus 4e, so that's 2e plus 4 over e, 4 over root e. And that, of course, means it's e 2e to the power of 3 over 2 plus 4 root e over e. Okay. That may cause some issues. Let's see. So if you put all of this together, so we've got area 1, which is negative 6, plus 8 root e, and then plus 2e squared all over e. So we appear to potentially have made a mistake with this one because everything else matches up. So let's try and see if we can find out where this one crept in. So there's 2e. Right. So indeed, when I put this all in one fraction, I put it over e. So that's multiplied by root e, but this should be multiplied by e. So that should be e squared. And then, of course, r, which is both of these added together. So let's minimize these. Will then become what we wanted. So this is area 1. This is area 2. So noting that r equals area 1 plus area 2, which is negative 6 plus 4 root e over e plus 2e squared plus 4 root e over e, which is then just 2e squared plus 8 root e minus 6 over e. And you can factor out the 2, which is e squared plus 4 root e minus 3 over e as required. And that's how you do the question.